Swayam Prabha. Digital India. Educated India.
So this two variable function needs to be minimized, okay, and we are going to start with the point -3 -4. So it's x1 x2 and x1 x2 space, that's a point, that's my initial solution. And you can think of this is some problem where this is my objective function that I have modeled, and I have an initial starting point which is -3 -4. I will do a line search that needs to be performed along let me first make this a little bigger, along 1 1, okay. So along the direction 1 1 using bounding phase. So basically if I take the chalk, what I have is I have a two-dimensional space x1 x2. I've got a -3 -4 point and I'm going along 1 1 direction, okay. And objective function can be defined anywhere in this space. Somewhere there will be a minima. I need to find that. So we talked about this directional search. So use first A is bounding phase to bracket. Can you bracket the minima? A lower bound and an upper bound along that line. So the only thing is the distance. If this is x, so distance, this is the x, this point. So x is my variable. So this x is not as x1 x2. x1 x2 are these two. X is in this. Oh, we got the volume now coming here. Okay, good. So how do you do bounding phase? Do you remember? So I want you to use Excel for this. Go to your let me see here. So you can go to your Excel sheet, Excel page, and okay, one thing I didn't give you, I think this is the old one. Yeah, put a delta equal to 0.2. That is missing in the code, in the question. You will use delta equal to 0.2 because you need an input, and x naught is already. So what will be x naught here? It's going to be 0 because I'm starting from here going in that direction. So x value is going to be 0. So you see now what I did. This is the solution, but you have to do it yourself. So first thing I do is I go. What is this one? One second. Is it the right one? 0.2. Yeah. 1 0, yeah. So 0, 0.2 and 0.4, but I did that and it looks like it's missing here. So first thing you need to figure out is direction, but in this case, since the direction is given, I don't have to check the initial thing which way to go, because I've already told go in that direction. So that's why I think we don't have to do finding whether delta should be positive or negative. Delta is always positive. So straight away apply the bounding phase. So this is 0 corresponding to 0. Then we move to 0.2 along this. This will be my x1, and then I move to 0.4, and that will be my x2. So if you go to Excel, you see I've got 0 and the corresponding x1, x2, can you find along that direction? Is -3 -4, and then corresponding function value. See, I've coded the function value. This comes from x1, x2. So x1 square minus x2 whole square plus x2 square. That's the objective function. I've coded and I get the value here. Okay, then move to x2, a equal to 0.2, delta distance away, and then how do you find the corresponding value here? What is the corresponding xy, x1, x2 value? How will you find this plus that a times or x times 1 comma 1. So that is what I have gotten here. So this is -3 for x1 plus 1 is the direction times b4. Okay, b4 is this. So I get the x1 value here, and then similarly I get the x2 value there. So basically it's a vector operation. You have this and you want to go along that direction by 0.2. So figure this out, x1, x2, and once you know x1, x2 you can compute it. So you basically have to drag it and you get corresponding x. Now that I got these two, I compare the function values. Which is better? 2 is better. because it's reduced the function value. So then I apply the bounding phase formula. It will be this one plus 2 times 0.1. So it will be 2 times 0.2, which is 0.4 plus 0.2, 0.6. And now you can get the corresponding values of x1, x2 and the function value. This is still better than that. So I go one more. Now I'm going 0.8 away from 0.6. So 0.2, 0.4, 0.8, 1.6 and then 3.2. Like that you exponentially go, and corresponding, you see we came here, and then when you go to the 6th step my function value has increased, so that's why I'm going to stop. And now what will be the bound? Bound is going to be 1.4 to 6.2. So that's my bound. Corresponding x vectors are given here. Minus 1.6 to minus 2.6. This is x1, x2 to 3.2 to 2.2. And the function values here are 33.386 to this. And if you can compute the optimality, the optimum, it's actually around, it's 3. A star is 3. So you see it's within this range. Okay, so that's the A part. And the B part is the golden section search. You need to get these bounds of 1.4, 6.2 coming here. So that's my lower bound, which is at 1.4 away, and this one is 6.2 away. And the optimum is around 3, I think. So its optimum is in between. So it's bracketed well. Now we need to do golden section of 3 iterations of golden section within that. So here are 3 iterations. So you have the low and high. You see now this 1.4 has to be mapped to 0 and this one has to be mapped to 1. And I showed you a formula, or you could do that. So that's mapped to 0 and 1. And the corresponding A1, A2, I call G1, G2 is 0.382, sorry, the golden section G1, G2 is 0.382, 0.618. And then you get the corresponding A1, A2 in this space. So 0.382 corresponds to 3.283 somewhere here, and 0.618 corresponds to 4.366, which is somewhere there. Okay, and now that you have A1, A2, you can find x1, x2. Okay, you find x1, x2, and then once you know x1, x2, you can compute f using the original formula, and uses x1, x2 and gives you the function value, right? Okay, and now that you have the function value here, and the second point x1, x2 are these two, and when you do the function value, okay, so now you see this is the first point, f value, and the second point f value is the next one. So which is better? Which is rather worse? 2.386 is worse. So G1 is better than G2, so I'm going to delete this region. Okay, so I'm going to have my search from A to this now. So how do you do that? In the next iteration, you see my lower bound is still 0, what I started with, and then my upper bound is now 0.618. Previously it was 1. So this is 0 and this is 1. I had my whole thing. Now I eliminated this, so this was at 0.618. So now my upper bound is also 0 to, I'm sorry, upper bound is 0.618. So I do that, and all these things are kind of, I just copied from here, and the new point is found 0.236, which is 38.2% from one end. And then this is the other one. You see there, one of them is always matching. 1 point from before is now the same, and also third iteration, 1 point is same as the second. One is always new, and you compute all of them, and then you find which is better, and you have to eliminate the remaining part. And then third iteration at the end, you get, so if I want to see what is my A value, you see it's 3.233 to 3.666. So we started with, sorry, not this, the range, started with 0 and 1. Now after 3 iterations, we have 0.236 to 0.618. So we have actually reduced. So we have come very close to the bound now, to the actual optimum now. Okay, if you keep running for a few more iterations, this will narrow down, and eventually when they are within 2 or 3 decimal places, you can stop. So try this in your way. This is my way of doing it. Excel is a good way to do, because you can put the function value and just drag down. All you have to do is figure out how to get these 2 points. One is at 38.2% from this end and 61.8% from the same end. You get these 2 points always, but it has to be that percentage of these ranges that you have. Initially you have 0 to 1, then we've dropped it by 38.2%, and then dropped again by 38.2% of this range, right? So if I took another thing here and say equal, where is the equal, okay, I would take the two range difference, so this minus this, okay, I get 1, the difference between the low and high, and I'm going to drag it down. You see, this one is 61.8% of the first one, and then 61 of 8% of 61.618 is 0.382. So if you keep on doing this, this range is going to reduce, okay, and eventually it will be so small that you can quit. But in this case, the optimum will be at x star equal to 0. These values are going to go to 0 and 0. You see, already they are close, it's getting down. Only 3 iterations, so you need maybe 3 or 4 more iterations to get down to a good value. Okay, so if you're interested, you can try more than 3 because you'll have the code, you just have to drag it down. You need to make this decision here, which part to keep, which part to delete, and then you can do that. So you'll have a good experience with these 2 methods. Any question here? No? Let's sit here. Okay, so the bounding phase was over here. So basically you start with 0 as the A, then you go 0.2 and look at the function value. Since this is better, you have to continue. So now go 0.4, 2 times delta, and then it's still better. You go 4 times, you go now 4 times delta from here, which is, we go 2 times here, and we go 4 times here. Now we go 8 times from here. So 8 times 0.2 will be 0.8 added to this, and then we go 1.6 is added to that, and then 3.2 is added to that. So that's how you go. And every time you compute the function values, and when it increases, you stop. You've gone too far. Okay, then you take the previous one and the last one as the bound. Okay, and that bound is used here in your golden section, because golden section needs a A and a B, and that comes from the bounding section. Is that okay? You can try it. Okay, so I'm going to not save it. Okay, no, rename the files. No, yes, I want to view these files later. No, remove these files. Okay, that's fine. Okay, so all right. Next question is about the f-min search. So this is without constraint. Okay, and here is the function. It's a 2-variable function again, and then you start with 0 and 0.8 and to find the minima and display the iteration-wise values and report the function values. Okay, for that we need to go to MATLAB because MATLAB only has f-min search. So oh, I don't have the MATLAB here, right? Or Dipanshu, how do I get access to MATLAB? You have already put it here. Open the MATLAB environment for me. Where you are? Okay, here. Okay, so here I need to open. I have the code here. Open. Oh, it's on this computer, so you'll not be able to see it. Can we have this directory? Not new. Just try open again and do this open on top. Yeah. Now go to this computer. Okay, but let's see, can we access to this because you are here, you'll probably not be able to, right? These are all your stuff, but from here we cannot choose anything else. Okay, so then we need to maybe transfer it. Yeah, upload those 2 MATLAB files. Sure. We'll figure this out for tomorrow a little better way. Okay, so it's already here. Files, choose files, and from mtech. No, yeah, this one, yeah. And these M files, these 3 M files. Yeah. Okay. Question 2, 3Q. Okay. Now go to your MATLAB. Yeah. Open your. Yeah. Those are the ones. First 2. Yeah. Double click. I hope it runs. Let me first see if it runs. Yeah. Nice. Okay. So let me explain what I've done here. Are you seeing it there? I don't know if I can increase the size of the font size here. Are you able to see? Very small, right? Windows Plus. This is the MATLAB environment. Sorry? Oh, yeah. Good. Little better. One more. Okay. Okay, first let's, so this is the objective function, I hope. Is that the one you have? 2x1 square minus 2x1 x2 plus x2 square plus 2x1 minus 2x2, right? Okay. So you first define the function. This at x is needed to define that it's a function of x. X is a vector. x1 is the first component, x2 is the second component. That's how MATLAB does it. I hope all of you know how to use MATLAB, right? Okay, good. MATLAB is an engineer's language, so you have to master it. This is the new point, a current point, 0 and 0.8. And then this option, I'm just saying, please display iteration wise how the function values is reducing and ultimately plot them. So this is the way to do it. You can look at it on the MATLAB. So if you go there and search for fmin search, it's going to show you all of these. Then this is the command for MATLAB fmin search. Note objective function, x0, and option. Okay, these 3 I have defined. And now I'm going to print the fmin search result x vector, which is x1, x2, which is output here, right? And then the fval, which is the function value. So when I run it, you see this is the result I get. It just gives some condition of how it has terminated. Okay, let me run it again. Okay, right from the beginning. So this is where it starts running. It shows iteration wise, function count 1, one evaluation is done. This was the function value. Second iteration, it took 2 more to do whatever it does inside, and it has improved the function. See, minus increasing means it's minimizing, right? And then 2 more, 2 more, 2 more like this, and it's improving, but almost got stuck. It's still doing, and then -1, and it has a termination condition already set up. And this is, it's telling you what the simplex search is doing. In expanding, I've talked to you about expanding. When you get a better results, then it contracts inside, contracts outside, depending on the situation. It's telling you just reflection sometimes is good. So all this it's doing, and eventually it's stuck here, and it's reporting the result 0.1, and function value is -1 for that solution. If you want, you can use the derivative concepts with the original function, 2 variable function, and show that this is really the minimum. Okay, you do the derivative equal to 0, and then second derivative will give you a matrix and show that at this point the matrix is positive definite, which means if you compute the eigenvalues, again MATLAB can give you the eigenvalues will be all positive. That's how you say your matrix is positive definite. So that's an extra work, but if you don't want to do, just show the results. Okay, so it's a simple kind of code you have to write. Just try to understand what is, so if I show you what is fmin search, F mean search. Should take me to internet and finally to, okay, here I don't want all this. F mean search. Okay, here are the syntaxes. Come on, it's asking me to say where I am. Where is India? India. Maybe it's happy with that. Okay. Here are all the so here are all the commands. F mean search. There are several things you could do. Just fun and x naught are minimum things. The objective function and the current point. You need these two, and then search will start from there. And then there's options you can choose. There are other things, but we never use some of those. There are exit flags and all that to see how well the algorithm did. Here are some examples. So you see, if you want to optimize this function, this is how you define x naught and then call for these and you get the result. Okay. If you want to plot, here is the plot function which I showed you, right? And then you have to call options along with that, options, and then it runs and it shows how it's running. So this is how it is. Okay. It's very nice. So there was a plot, I don't know where it went. So you see that somewhere? Left hand side? Yeah. Oops. This one. Doesn't work. Dipanshu, do you know what to do? There's a plot which you have to show them. We can rerun. Yeah, bring it up. Okay, so you see how it shows this when you give the plot command, it shows where it started from, function value, and how it drops. You see, very quickly in about 4 or 5 iterations, it's almost there. And then for last few steps, it got stuck at -1, and it's not seems to improve. And then it figures that's the optima. But here it was at 0.99998 minus and still continued because it thought there may be some more better solution and it found one. So it has its own termination conditions. Okay, so sometimes this is good to watch to see how fast from initial point you have come. This is called rate of convergence. Okay, if you do this in log plot, you can see that very fast it comes down. All right, so that's the second one. Now I'm going to open the third one. Open. This was again on the here somewhere, third one, but probably I wanted to, yeah, there's third one. Okay, so let me show the simple one first. So third one, okay, let me go to the third one. Question first. Question. Okay, so this was the F-min search. Third one is F-min con, now with the constraint. So I have two constraints. One is less than, other is greater than, and bounds are there for every. Objective function is also different, minimize. Start with 0, 0. Now linear constraints we can express in ax less than equal to b. Okay, ax less than equal to b, we could do that. Let me see if I can. I mean, fourth one we are not going to do today, we have not covered. Yeah, ax less than equal to b. Locate the minimum solution graphically by sketching the feasible region. So for this you need to do a bit more, or you could do it by hand using some other plotting software, and show the F-min con solution and the feasibility, because this is for you to understand what's the feasible region, how the algorithm has done, and so on and so forth. So now let me go to MATLAB. Where did I click it? Chrome. So look at this constraint. This is a linear constraint. So I can use ax less than equal to b. So if I convert them into a times x less than equal to b, what is my A matrix? Coefficient of x1 is 2 but it's greater than. I probably didn't tell you. When it's greater than, you want to convert into less than, because fmincon wants you to do less than equal to, right? So we can multiply both sides by -1. So then the sign will change to less than equal to. So this will be -2, this will be +1, and this will be +1. When it goes to the other side, it will be -1. So -2x1 plus x2 less than equal to -1. That will be the constraint in less than equal to form. A matrix is going to be coefficient of x1 comma coefficient of x2, which will be -2 and +1. So I've got -2 +1 for the coefficient of A, and B is going to be simply -1. I don't even need this bracket, but it's fine. When you have multiple equality, then you need the bracket and you put a semicolon after every row to go to the next rows. But here we have just one linear inequality constraint, so that's why I have just one row. Make sense? So the MATLAB considers is like A times X vector less than equal to B. That's what this will give you. Any doubt? Just for those one who has some doubt. So my A is -2, 1, and my B is -1, right? So my MATLAB requires AX less than equal to B. So let's try that. -2, 1, X is x1, x2 is a vector, less than equal to -1. So what is this equal to? -2 x1 plus x2 is less than equal to -1. So this is the equation I have, inequality, and I can represent it like this, where A is this and B is that. Okay? So that's what we've done here. And then I don't have an equality constraint, so I put null. These are null in MATLAB. Nothing there. Lower bound vector for x1, x2. x1 is -2, x2 is -6. So this is the lower bound vector. And this is the upper bound vector, 8 and 6. 8 for x1, 6 for x2. Okay, these are both lower bounds together, and these are both, you can put comma, you need not put comma, doesn't matter. Here I have given, here I forgot to give, but doesn't matter in MATLAB. Okay, now I start with 0, 0, so I specify x0, 0, 0. I put the option because I want to see iteratively how the function value is reducing. I want to plot, like in the fmin search. This is commented, so yeah, if I don't want to see all of these, I can sometimes do without that. And then this is the fmincon routine. First, the objective function. Here, I could have done the previous way, obj equal to @x and write the function. I have decided to do a sub function for objective. Then you have to put this @objective, and this is my objective function, where I say f, I'm returning f through this function, where x1 minus 1.5 square, you see that one here, plus x2 minus 5.5 square, right? I write that here, and so this is like a subroutine. So that's the objective. x0 is given, a and b are given, equality and b equality are also given, they are null. LB is given, lower bound, upper bound is given. This is the format. And constraint, I now define the constraint, another sub function. Now this has inequality and equality is the constraint. X vector comes in, and see, there is only one constraint I need to define, which is this nonlinear constraint. It will always have to be less than equal to. So 4 times x1 plus x2 square minus 25. 4 times x1 plus x2 square minus 25. And that's my C that goes. And there is no equality nonlinear constraint, so I put it as a blank. If there are more constraints, I will define a C1, this C2, this, and then make a vector C equal to C1 comma C2. So everything works in vector in MATLAB. This is a vector of constraints, this is a vector of equality constraints, but I have only one here, nothing here, so this goes as a constraint. Option, again, it plots and puts the iteration-wise results. This is the simplest code that you can have for doing unconstrained minimization using MATLAB. Okay, so now all you have to do is run. I have to move this up. Yeah, the plot comes up. Why this side is different? It's not in the MATLAB. Okay, let's look at the plot. So this is started from here, and it dropped in first iteration. Then it went up a bit, and then it stayed there, and that's the minimum. Why did it go up? usually in the F-min search we saw it was monotonically non-increasing. It can stay the same but never go up. Here, constraint, why does it go up? This is the function value, remember. This point is not feasible. Okay, it's a good function value, but it's not feasible. But then to get the feasible value, it has to sacrifice the function value a bit. But now it has found the feasible and the best value, and it's after a few iterations it stops. Okay, now that you've seen that, let me see if I can show you what is here. So this is HA2. Iteration wise, you see again, this is question 2 now. I need question 3. Where is question 3? This one, question 3, right? So here is the function value reducing. You see, initially it took 3 function evaluations, then 4 more, then 3 more, then 3 more. This one is using, I think the default is trust region method, which we haven't talked about, but it's a complicated method. It will take me like two lectures to cover it. But it's a complicated method, but it has a lot of things happening with the search is within a trust region and all that. These are their latest sophisticated method. They always put it here. Okay, but you don't have to worry about it. If you're using this, just run it. It shows feasibility. 0 means it's feasible. 1 means anything positive means it's not feasible. And 0 means feasible. So first 2 are not feasible, and then we get feasible. You see, it's still kind of function values are still improving, but they have a termination condition. It says actually local minima found that satisfies the constraint. Okay, then it says how it has quit, stopping criteria details. Now this is the result that I wanted it to print here, F-min con result, xvac, and the function value. This is the x vector. I guess it's supposed to be 2.5 and 3.9, but it's quite close. And f star is 3.465. Okay, so now this is the constraint result. All right, so that's that. And graphically also, okay. Now if you want to draw the feasible region and the contour of the objective function, you need to beautify the code a bit more. You have to do a bit more. I'm just going to show you, but I'm not expecting you to do that. If you do this, maybe it's a 2 variable thing you can do on your graph sheet. On a graph sheet or using another software, you can plot the feasible region by taking the 2 constraints and show this. So I have another code here for that. Open. I think it's this one. Let me check. Open. Okay. Now what this has is this extra bit of coding. It actually plots and everything. It does the contour here. And this next part is the same. The F-min con part is the same. And when I run it, let's see what happens. Okay, this is one of the same plots. There should be one more plot. Where is that? Let me take that away. Here. It took some time. Okay, you see that, right? So you see there are 2 constraints I've got. And these are contour lines of the objective function. As you go this way, your function value increases. So this would be the minima. Because in this feasible region, this one is closest to this 1.5 and 5.5. The contour function says as you go this way, your function value increases. So this is the best solution. And this is around 2.5 and 3.9 or something like that. Almost 2. What was it? Anyway, it's close to that. And the algorithm started from here, which I provided 0, 0. And it went pretty close already in the first, but it was infeasible, as you see. It's outside. And then it went in, very close to that. Now, if you give another, it's good to try. If you just change the initial point and see, maybe give something here or here, you can see that it will go in and then come there. And so it's nice to see. In 2 variables, you can only do that. Right? So you'll get a good idea if you do an extra bit of running to see how the algorithm is working. You get a pretty good idea how these algorithms work. But I'm just expecting you to So fourth one, we'll include it for the next, for tomorrow, because I have not covered the schema part. First part you could do, but the B part will not be able to do. Just in the theoretical one, I couldn't finish today. So we will assign the whole 4 for tomorrow. Okay? So do the first 3. I hope it's clear. This is point-based method only, bounding phase, golden section, and then we did the fmin search of MATLAB, and then fmin con with constraint. Fmin search is without constraint. So these, once you have little practice, you know how to solve unconstrained or constrained optimization using MATLAB. And believe me, this is going to be very, very useful when you do your PCs on something and you have to optimize some function. This is the best value you can use this. You know how to use it. Okay?